Today we're going to talk about radicals in a different way. We're going to go over dividing. And dividing, instead of just dividing numbers, we're going to talk about fractions, because we know fractions means to divide. One rule we have to remember, and we will start with our first example, is that you can never have a square root in the denominator of a fraction. All right, we will never leave an answer like this, 2 over the square root of 5. So we want to get rid of that square root in the denominator. We don't know the square root of 5, so we need to figure out how we can do that. And there's a process, and we know that we can multiply anything by 1. That does not change our fraction. We can multiply anything by 1. And we know that we can write a fraction as 1 over 1. That is the same thing as 1. But you can also see that that doesn't really help us get rid of that square root in the denominator. So what we're going to do, instead of using 1 over 1, we're going to multiply by the fraction square root of 5 over square root of 5. If we look at this new fraction, we see that that's the same as 1, so it doesn't change our answer in terms of what the number is, just in how it looks. When we multiply fractions, we multiply straight across. 2 times the square root of 5 is 2, keep it outside, square roots of 5. The square root of 5 times the square root of 5, well, that's the square root of 25, which is just 5. And just like that, we eliminated the square root from our denominator. And if we put either one of these, either the first fraction or our final answer, into a calculator, we would get the same decimal answer. So we have now simplified that fraction. Let's try another one. What if we had 5 over the square root of 6? Again, we cannot have square roots in the denominator, so we're going to multiply it by a fraction that needs to be equivalent to 1. Well, if you said square root of 6 over square root of 6, you are correct. That gives me 5 square roots of 6 in the numerator and just a 6 in the denominator. What if we saw a fraction like this, where it's a big square root of, we'll do 5 over 8. If the whole thing is a square root, well, that just means that the numerator and the denominator have square roots. The process is the same. Multiply by a fraction equivalent to 1 that will get rid of the square root in the denominator. For our denominator, square root of 8 times square root of 8 is square root of 64, and that is just 8. And this should always happen. This should always get rid of our square root and just be that number. On the top, square root of 5 times square root of 8 is square root of 40. Now you should be saying something in your head about, hey, I think square root of 40 breaks down. And it does. Square root of 40 breaks down to square root of 4, square root of 10 over 8. The square root of 4 is 2. Square roots of 10 over 8. And do you see it? Do you notice that the 2 and the 8 reduce to 1 and a 4? That gives me square root of 10 over 4. Do you think anything there can reduce? No, you should not think that it reduces, because the 10 is in the square root, the 4 is not. So those cannot reduce. This is my final answer. Let's try a slightly different problem. Square root of 5 over 2 square roots of 3. Well, we see a square root in the denominator, the square root of 3. We cannot have that. We're not going to worry so much about the 2 right now. So let's just do the same thing as before and multiply by the square root of 3 over the square root of 3. In the numerator, square root of 5 times square root of 3 is square root of 15. What about my denominator? Well, the square root of 3 times the square root of 3 is the square root of 9. That's just a 3. 2 times that 3 would give me a 6. Because the 15 is inside the square root, the 6 is outside of the square root, this does not reduce. That is my final answer. What if we had a cubed root? We've been doing cubed roots. So what if we said 3 over the cubed root of 4? Well, you might be tempted to say the cubed root of 4 over the cubed root of 4. You'd say that's easy, Mr. Repka. But what happens when you multiply these two? Well, you'd get the cubed root of 16. And do we know the cubed root of 16? No, we don't. We do not know the cubed root of 16. So that didn't help us. I would still have a cube or a radical in my denominator. So what do we do? Well, let's look at it this way. This 4 has an exponent of 1. And if we think back to when we did variables, the easiest way to have an exponent that we knew the cubed root of was to have that exponent be 3. Because we know the cubed root of x cubed is just x. So if I need a total of 3 exponents, what do you think the exponent for this second fraction is going to have to be? The 4. Correct. The 4 would need an exponent of 2. Why? Because now I have the cubed root of 4 to the third. Because we add exponents when we multiply like bases. The cubed root of 4 to the third, that is just 4. Just like the cubed root of x cubed is just x. Or if you wanted to do it, you could say the cubed root of 64, and that is just 4. Our numerator, the process is the same. Since the 3 is outside of the radical, it just stays outside. And it's up to you. Do you want to write 4 squared, or do you want to write 16? I do not care. Does anything in this fraction reduce? No. The 16 is inside the radical. The 4 is outside. This is my final answer. Let's try one more with the cubed root. What if we had 8 over 5 cubed roots of 3? Again, we can't have a radical in the denominator, so you should by now realize we at least need a fraction with those cubed roots. You know it's going to be a 3 here. But if we leave it like that, we would multiply these and get the cubed root of 9, and we don't know the cubed root of 9, so that does me no good. So maybe it helps to write our exponents. The 3 has an exponent of 1, so over here I need an exponent of 2. Now in the denominator, cubed root of 3 squared, well that's like the cubed root of 3 cubed. That's just 3. Take that 3 times this 5. That gives me a 15 in the denominator. My numerator, my 8 stays in front of the radical. And again, you can write 3 squared, or you can write 9. And nothing reduces there. These are equivalent. So if we said cubed root of 16, or I'm sorry, the square root of 16 over 2, we know that's the same as the square root of 16 and the square root of 2. Now, do you notice anything? Well, you might have jumped ahead and said, well, we can multiply square root of 2 by square root of 2. But hopefully you notice that looking right here, since the 16 and the 2 are both inside the square root, or here it's very obvious they're both inside the square root, we can reduce this fraction because they're both inside the square root. So we could just change this problem to the square root of 8. Well, we know the square root of 8 breaks apart to the square root of 4 and the square root of 2. So 2 square roots of 2. But what if we didn't reduce? Let me do that if we didn't reduce. So you said, all right, Mr. Repka, I didn't notice that that reduced. And I just broke it apart, and I multiplied it by the square root of 2 over the square root of 2. And I said, hey, that's the square root of 32 over 2. I'd say you're right so far, but you're not done. You should see that the square root of 32 is the square root of 16 times the square root of 2 over 2. Whoops. The square root of 16 is 4 square roots of 2 over 2. And now, since the 4 and the 2 are both outside the radical, these can reduce to 2 and 1. So we get the same answer. It's all about how we get there. I would suggest if a fraction reduces right away, like this one, to reduce it, because you have smaller numbers. And in general, we're fans of smaller numbers.